Good morning, students. Okay, so all ready? Is my voice clear? Is my voice clear? All right. So let us begin with the second online live lecture of BEE. What did we study yesterday? We studied the behavioral pattern of R, L, and C when they are placed in an AC circuit. We'll do a quick recap of what we have studied yesterday. So you remember, for a resistor, what was the impedance? That is more important. What was the impedance? The impedance is given as, or it is represented by Z, and it is given as Vm upon Im. And it came out to be Vm upon R. These derivations were done yesterday, so it came out to be R. In case of L, the impedance came out to be Vm upon Im, which further got expanded to Vm upon omega L with a minus J, where J is iota, which is 1 angle 90 degree. So finally that Z came out to be plus J omega L. In other words, it was plus J XL, where XL is equal to omega L. Is that part clear? Similarly, for the capacitor, the impedance is given as Vm upon Im, which in turn becomes Vm upon plus J omega C Vm. So that came out to be minus J 1 upon omega C, which is minus J XC, where XC is equal to 1 upon omega C. So these were the important derivations that we had done yesterday, and these are the formulae that we had derived. So today we will study, before we move on to our next topic, we need to understand a bit more about this J thing, because I had gone through your comments yesterday and few of you had doubts with this J thing. I hope you are all clear, like what is this J? This J is the iota, which is 1 angle 90 degree, or it is the positive square root of minus 1. Is this thing clear? Now with the introduction of J, we are no longer into the real plane. We actually come back, or we get into a domain that is called as complex domain with the introduction of J. So if you start plotting a complex plane, then it looks something like this. The x-axis is represented by the real axis, whereas the y-axis is represented by the imaginary axis. I hope you are all clear with this thing. Yes, Omkar has a query. that in Ravish Singh textbook, they take phase positive, and even though current is lagging with respect to voltage, whenever you take a phase, you please take it as positive. And if the current is lagging, then you need to write in bracket whether it is lagging or leading. This part was told yesterday in the class, that you keep your phase difference or the phase as positive. Do not take it as negative. But if the current is lagging, then you please write it in bracket that it is lagging, and if it is leading, then please write it in bracket that it is leading. So this is the complex plane, this is the real axis, and this is the imaginary axis. So this imaginary axis is actually represented by the iota. This represents plus j and this represents minus j. Is this part clear to all? So this is how the j is placed in a complex plane, and the x-axis is taken up entirely by the real axis. And j has only one magnitude, that is unity. That is one angle 90 degree, or it is either one angle minus 90 degree. It could be in multiples of 90 degrees. And the magnitude always remains unity. Now over here, similar, we will be putting an analogy in our electric circuits. We will have a plane that is called as impedance plane. Now what is this impedance that we have already studied yesterday? It is represented by Z, and it represents the total resistance and the total reactance that is present in the circuit. And this reactance is being given by the presence of the inductors and capacitors, which in turn generate inductance and capacitance in the circuits. So how will this impedance plane look like? The impedance plane is similar to that of the complex plane, with the x-axis represented by the real values, and those real values are represented by R. And similarly, the y-axis is an imaginary axis which is represented by the reactances. So plus jx is along the upward direction of y-axis, minus jx is in the downward direction of the imaginary axis. Now this upward direction is actually the reactance that is imposed by the inductors, that is the inductance plus jxl, and in the downward direction it is the reactance that is being given by the capacitors, that is the capacitive reactance that is given by minus jxc. Is this clear to all? Now the question is, why is this inductive and capacitive reactance included in the imaginary axis? Why are we including? Why is this reactances included in the imaginary axis? That is more important for us. So let us study a bit more about these reactances. Now, as yesterday we had studied, for a resistor, V and I are in phase, isn't it? Since V and I are in phase, the work done by V and I is real. Why do we say it is real? Because it directly converts electrical energy to heat energy. I'm repeating it again. For a resistor, the voltage and the current are in phase. Hence, the work done by a resistor is real. It directly converts electrical energy to heat energy. Whereas, if you consider an inductor or a capacitor, over there, the voltage and current are not in phase. They have a phase difference of 90 degrees. For an inductor, I lags V by 90 degrees, and for a capacitor, I leads V by 90 degree. Hence, for an inductor and a capacitor, the work done is not real. It directly does not convert this electrical energy to heat energy. Rather, what does these two elements do? They help in converting that electrical energy into fields. This inductor will help in the generation of a magnetic field, and a capacitor will help in building up an electric field. And why are these fields being generated? Because there is a phase lag. There is a phase lag in both these components by 90 degree. And as the work done by them are not real, you cannot represent these phase differences by scalar representations. This phase lag cannot be represented by scalar representations. So what do we need over here? We require vectorial representations. We need vectorial representation to show this phase lag of 90 degree that is generated in between the voltage and current for an inductor and a capacitor. So how will we do this vectorial representation? Since there is a phase difference of 90 degree, whether it's a lag or a lead, we take the help of this J. J, which is iota. Either it's one angle 90 degree or it's one angle minus 90 degree. And hence we generate this impedance plane. Along the x-axis we will have the R, whereas along the y-axis it will be an imaginary axis, or you can say the complex concept being introduced. You will have the plus J element over here, the reactance part, which is plus JXL, and for in the downward direction of x-axis you will have minus JXC, which is the capacitive reactance. So all we can see is this plus J and minus J present you with a mathematical tool or a mathematical analysis to understand this physical phenomenon. Now, is this clear? Are we clear up to this part? That why are we representing this inductive reactance and capacitive reactance in an imaginary, along an imaginary axis? Is this part clear to all? Why are we actually introducing this concept of plus J and minus J for an inductor and capacitor respectively? Please let me know. Is this clear to all? Any doubt so far regarding this J concept? Now you got to know why we require this J. Without this help of this J, we won't be able to represent the concepts of inductors and capacitors on a real plane. We have to take help of a complex plane, as the work done by the inductors and capacitors are not real. Not real as in they do not convert the electrical energy to heat energy directly. Rather, they first help in the building of the fields. And yes, there is one more thing that you need to Remember as well, I am telling you this thing that the work done by the inductors and capacitors are not real. So we have got another name to it. The work done by the resistors, that is called as real, whereas the work done by L and C is termed as reactive. Not real in electric circuits is termed as reactive. The work done by the resistors is given as the real power, as known as the real power or active power, whereas the work done by an inductor or a capacitor is not real and it is being termed as reactive power. Is this part clear to all? Can we move on and can we start solving questions? Okay, now before we start solving questions, we need to know two more things. Now there is one L and there is one C. Now when you shall be solving questions, yes, one more thing that you need to take into consideration is we are studying about all these components R, L and C for an AC circuit. So far these circuits or these components shall be connected in series. We are not discussing any other connection as of now. We are only considering the series connection of R, L, C. We would either study right now RL or RC or RLC. And you must be clear about one thing, that the impedance that is being shown by R is the resistance itself. The impedance shown by L is plus JXL. The impedance shown by C is minus JXC individually. Ameya is asking what is the significance of XL and XC. XL and XC are the reactances that are being shown by the components, that is inductor and capacitor. Inductor itself is a coil and capacitor itself are the charged plates. But when they show their reactances, they have another factor included or involved in that, and that factor is the angular frequency or the frequency that comes into the picture. The frequency when multiplied with their property gives you the reactances. Alright, I'll see to it that I can share these sheets. As these videos are available, you can go through them once again as well. I'll let you know about that. So before we move on to solving these questions, what I was trying to tell you is, in the question, when you start solving, it would be written like a resistor is connected in series with an inductor. This is the basic phrase that you will find in the question. But at times, this may not be the wordings that would be used in the questions. So there are two words being used for representing the inductor. The first one is, you could have something written as inductive impedance. If it is written as inductive impedance in the question, then it is a normal coil. That is an inductor. Or if it is written as a non-resistive inductor, then it is again represented by a single coil. But if you come across this term, something called as a coil, then it is no longer only represented by a coil. A coil means having a small resistive part in series with an inductor. This is how a coil is being represented. Or there is another word for this coil as well, that is called as choke coil. You will have a resistor in series with an inductor. So there are two ways in which this inductor could be asked in the question. Either it could be only inductive impedance, so it is a coil, or it could be a non-resistive inductor, so it is again only a coil. But if this term coil is mentioned, then it will have a small resistor in series with a coil. Or if it is written as a choke coil, then again it is this thing. Is this part clear? Similarly, for a capacitor, if it is mentioned as perfect capacitor, then it is only a set of charged plates, or if it is mentioned as capacitive impedance, then it also represents this a set of charged plates. But in case if it is mentioned that it is a capacitor with a lead resistance, I'm repeating it here, a capacitor with a lead resistance, in that case you will have a small resistance in series with the capacitance. Clear with this part? Now let us solve a couple of questions before we can move ahead to RL and RC circuits. Alright. So the first question is, given an AC circuit, it comprises of a pure resistor. I'm repeating, given an AC circuit, it comprises of a pure resistor having a resistance of 10 ohms, and it is connected across a supply of 230 volts, 50 hertz. Now you need to remember one more important thing. For an AC circuit, unlike DC circuit, the only voltage value cannot be mentioned. For a DC circuit, we only had the voltage values, like it is 10 volts, it is 20 volts. But for an AC circuit analysis, you will never be given only the voltage values, like 230 volts, 220 volts. No, since it's an AC circuit, the frequency has a very important role to play. So if the voltage value is given, you must have the knowledge of the frequency, because if this is not known, then you can never compute omega. And if omega is not known, then it's very difficult for us to compute the reactances. So this is a resistor having a resistance of 10 ohms, which is connected across a supply of 230 volts, 50 hertz. Now you have been asked to calculate the following. The first one is find out the current. Second one is find out the power consumed. The third bit is the power factor. So how do we solve these type of numericals? Now we are solving these numericals only considering one component at a time. This is only for our practice. Whereas in our examinations, we'll definitely have questions considering the combination of elements, not just considering one component at a time. So let us start with the solution. Is the question understood to all? Given a resistor having resistance 10 ohms connected across an AC supply of 230 volts, 50 hertz, we need to compute the following. Is the question understood to all? Okay, let us begin with the solution then. Now, what is this 230 volts? Now, we have a value given over here, 230 volts. When we did our analysis, we actually did our analysis from the sinusoid's point of view. That was the instantaneous representation where V was given as Vm sine omega t. That was only meant for our understanding purpose. So, what is this 230 volts? Is this Vm? No, it is not Vm. It is the RMS value of the voltage. It is the RMS value of the voltage. This thing is VRMS. This is not Vm. Because since we are studying only the steady state part in our syllabus, so we shall not be having the instantaneous values of voltages given to you. We will only have the RMS values of the voltages given to you. So this 230 volt is the RMS value. The analysis remains the same. There is no change in the solving approach or in the analysis part. The only thing that you need to know is this is the RMS value of the voltage, and since this is the RMS, then the I that is being asked to us is IRMS. Is that part clear? And rest all remains the same. Earlier, how did you figure out this impedance? Impedance is given as Vm upon Im. Now if I make it Vm upon root 2 upon Im upon root 2, will I not get VRMS upon IRMS? So these are the RMS values. Now how do we solve this? For a given question, what is the value of the impedance? And this is a resistive circuit, Z is equal to R, which is 10 ohms. How to find out this I? This I is basically IRMS. So it will be V upon Z, which is VRMS upon Z. VRMS is given as 230 upon 10, which is 23 amps. Is this thing clear? Now next is power consumed. Now we already know one thing, that if a resistor is involved in a circuit, then the work done is real. By work done it means the power consumed is real. This power consumed is real. And how is it given as? It is given as V into I, which will come out to be 230 into 23. Now coming to the last bit, I am writing it over here itself. The last bit says find out the power factor. Now what is the phase difference of voltage with respect to current for a resistive circuit? If voltage is along this axis, then definitely I is also along that axis. So the phase difference between voltage and current yes, the value is 5290. Vishwajit, you are correct. And what is the unit of power consumed? It is watts. This phi is 0 degrees. So what will be power factor? The power factor is the cosine of the angle between the voltage and current. So it is cos phi, which is equal to cos 0. Cos 0 is 1. So power factor is 1. Now moving on to another question. Now this question says there is an inductive coil. It simply says it is an inductive coil. Now since it's saying coil, that means we know that coil means it will have a small resistance in series with the inductor. But the question says it is an inductive coil with negligible resistance. So what will be our final component representation? The R value drops to 0 and there is only an inductor present. So the question says there is an inductive coil having negligible resistance with a value of 0.1 Henry that is connected across a 200 volts 50 Hertz supply. Is my voice clear to all? Connected to 50 Hertz supply. So these are the values that we need to find out. Find bit 1. Inductive reactance. Inductive reactance means it is XL. Bit 2. Find out the RMS value of the current.